So before we start looking at NAT, I want to kind of just bring you back to, we looked at this back in week 4, where you have your default classes of addresses. So, you know, your IPv4 addresses are split into 3 separate classes, A, B, and C, depending obviously where the first octet lies. So your class A is between 1 and 126. The first octet is between 1 and 126. Has a default subnet mask of 255.0.0.0. In other words, that's it, /8. Class B, first octet is between 121 and 128 and 191. So example 150.51 is a class B because the 150 is between 128 and 191. That's a /16. And your class C, the first octet is between 192 and 223. So for example, here we have 220. That's a class C, would be a /24. Now remember, when we're looking at the /8, /16, /24, that refers to the amount of network bits in the subnet mask. Yeah. So you're saying here that the first 8 bits of the address is the network part. So like 10.5.1.1/8. If I see this address here and a /8, right, I know that that means that this is your network ID, because each octet has 8 bits. So 8, 8, 8, and 8. Does that make sense? If I see 150.51.233.1/16, I know that that is my network part there, because the first 16 bits represent the network ID. Again, 220.1.50.63/24 would be 8, 16, 24, and there's your network part there. Okay, so this IP address 220.1.50.63 lives in the 220.1.50 network. That's kind of, hopefully we're all understanding of that there, yeah? Okay. So IP addresses, these IP addresses, they, you know, when it was first around, when they were first being developed, IPv4, they said, oh yeah, we're going to, this is give us, you know, roughly about 4 billion addresses. And initially, IANA, which is the company that it's called the Internet Assigned Numbers Authority, they constructed this, they put these together, and they said, yeah, 4 billion IP addresses is perfect. We're never going to run out of IP addresses with 4 billion. And then you had, during the 90s, you know, from kind of 95-ish onwards, you had the explosive growth of the internet, you had the .com boom, and all of a sudden engineers were like, oh, we're actually going to run out of IP addresses. So they came up with a system, best engineers, and the system was IPv5, and it didn't work, lots of bugs. So they threw that in the paper bin, and they went back to the drawing board, if you like, and they came up with IPv6. So there was IPv4, which would be news, IPv5, and IPv6. IPv5, obviously, like I said, was thrashed, didn't work, too much bugs, so IPv6. But IPv6 was designed, but they needed to come up a short to medium term. IPv6 is always seen as a long term. Okay, we'll move everything across in, you know, in 100 years time, everything will be on IPv6. But what do we do to address the current crisis of the lack of IPv4 addresses? So there was a task group put together, and there was a white paper called RFC 1918. Okay, RFC 1918. RFC stands for Request for Comments. And in this paper, they said, we're going to split. We're going to take the public addresses, and we're going to take each class of addresses, class A, B, and C, and we're going to split them up into separate different addresses. So we're going to have public addresses and we're going to have private addresses. Public addresses can be used anywhere. They can be used on the internet. They can be used internally, externally. They can be, public addresses can be used on the internet and internal networks. It can be used anywhere, okay? Now, the thing about public addresses, they have to be unique, okay? So public addresses have to be unique because they're a unique address on the internet. Private addresses are only usable on internal networks, internal into a company. When we say only use on internal networks, they are not routable out on the internet, okay? Well, each class, A, B, and C, there was subdivisions of those, or ranges within those classes A, B, and C, which were deemed to be, or which were separated as private addresses. And it worked on the premise that any company can have these addresses and they don't need to be unique, but they're not routable out in the internet. That's why they don't need to be unique, because they're not routable out in the internet. Okay, so for example, every address with a 10, any IP address at all with a 10 in the first octet is a private address. Because if you see, think about it for a second, right? Addresses, they run from 0 to 255. 0 to 255. So 10,000 to 10,255, 255, 255. That basically covers every single IP address within the 10 octet. If you add an extra IP address on there, you're going to go on to the 11 range. Does that make sense? So the 10 range is all private addresses, cannot be routable out on the internet. Then your class B private address range is 172.16.00 to 172.31.255.255. Okay, 172.16.00 to 172.31.255.255. So basically anything between 172.16.0 and 0 and 172.31.255.255 is private. So if you have something like, say, 172.29.16.3, that's a private address. Why? Because it lives somewhere between 172.16.00 and 172.31.255.255. Any questions on that? All right, okay. Class C, anything with a 192.168 is a private address. Anything with a 192.168 in the first two octets is a private address. So again, that will cover everything from 192.168.00 to 192.168.255.255. Okay, cannot be used internally, cannot be used externally. So what I mean by that is here. So let's say we have our fluffy white cloud, that is the internet here. Okay, and you have, well, I'll make this a router. And you have a LAN behind it. All right, so over here, the LAN is, let's say, is the 10 network. So you had an address here of 10.1.1.0/24. Oh. /24, yeah. So you had an IP address here, 10.1.1.1. Let's say 10.1.1.5. Okay, this is a PC. Okay, this PC wants to go out to the internet, you can route it as far as your company router. This is R1, okay? Let's say R1 has a connection to the ISP being Sky. Yeah. So this goes across this packet with a source IP address of 10.1.1.1, and let's say it's going to the internet. Let's say it's going to 3333. That's the internet. Let's say it's Google. Okay, destined to go to 3.3.3.3. What's going to happen is this packet hits our router, goes as far as R1. If our Sky ISP will see this, and every ISP has access lists, they've got route maps, they've got prefix lists, they have blocking. They will not allow this IP address, any IP address in the 10 range, to go out to the internet. Okay, they will be penalized financially if they do. Okay, and what will happen is Sky will connect to another ISP. So maybe Sky mess up, and there has been incidences before where the odd packets have been getting somewhat out on the internet with a private IP address. But if Sky mess up, or somebody messes up big time in Sky, well, it's only going to go to the next ISP. Sky will peer. It's called BGP peering. Sky may peer with, let's say, Virgin. Well, Virgin are going to block this because, again, all ISPs will not route these 3 ranges out. Okay, they've been configured to not do it. All right. And you're saying then, well, how does that, really solve our IP address problem? How does that, if you pardon the pun, address our issue that we're looking at in terms of we don't have enough IPv4 addresses? Splitting them into private addresses and public addresses will not work unless we add something extra, unless we do something extra from a technical aspect. So let me show you. Let's say if I log on here and I do command prompt and I do ipconfig /all. So my IP address here on this is my laptop or my desktop, 192.168.178.70. So you can see that that's a private IP address. So my house, if my laptop is, if I want to print, this is my laptop here, 192.168.178.70. My printer would be 192.168.178.5. Yeah. Well, if I want to communicate with my printer, well, I'm not going out to the internet because my printer is on a private IP address and this device here is on private IP address. So there's no issues. However, if I want to go out to the internet, then this IP address here will hit my default gateway and my router will take this IP address and request from my ISP, which is DigiWeb, a public IP address for a short time. So the internet does not see me as being 192.168.178.70. The internet sees me, excuse me, I'll just Google what is my IP address. The internet sees me as being here, 84.203.32.120. Yeah. So what happens is the process that this private IP address hits my ISP, and my ISP will take this address and change it into this public IP address just for the purpose of routing back to my ISP, and then the packet will get changed back into 192.168.178.70. Okay. Okay.
Will the public address change each time you log on, or do you use the same one for your IP address?
Sorry, Graham, when?
Yeah, see, when you are logging on to the internet and your IP address is changed to a public IP address, will they use the same IP address? Will that IP address be associated with your IP address, say, from your desktop?
Not
On
all
the
the
public,
time. It can change.
okay, right.
Yeah, it can change. It can change. So basically, and it's not unique. Okay, so this is a reason. Okay, so I'm like, let's say DigiWeb. Let's say DigiWeb has, let's say, 200,000 users in Ireland. Okay, there's not, DigiWeb doesn't have 200 public IP addresses to give out to every single individual connection. Okay, if that was the case, then there'd be no point in having private versus public addresses. This could be shared. Some other guy with DigiWeb could use 84.203.32.120. And that's what we're going to talk about now, network address translation. The process of changing an IP address from a private address to a public address and tracking that address back to its originator to change it back to wherever it needs to go. So when I send out a request, my packet here, 84.203.32.120, is going out to Google, let's say, for example. Someone else in, let's say, in Cavan could be using this same IP address going to Facebook. The internet or my ISP needs to keep a system in place to track that this is going to Google, the one in Cavan is going to Facebook. How does it do that? And we'll talk about that now. Another thing to do, let me just, 1 second here now on this. I want to just, just going to open up a couple of browsers here, okay? Okay, so here I have my IP address, Med-Éireann, the journal, and Independence, yeah? Okay, so if I go into here and I type netstat space -a, you can see lots and lots of connections. So you can see here, my IP address 192.168.178.70, and you see port numbers. Where am I going to? 50719, 20, 23, 24, 25, and so forth. Some of them are skipping, but these are only showing your established connections. So we do netstat -n. You can see it. So the reason we have port numbers, it helps keep the sessions separate. Yeah. So each session has its own source IP address, destination IP address, source port, destination port. We've known from, I think it was a week 2 or something, that the destination port matches the application. So 443 is typically HTTPS. It means that this is encrypted. 80 is HTTP. It means it's in clear text. So we got all these different sessions that are going out to the internet and have this information. The port is added on at the transport layer. Okay. Any questions on that? So your source IP address, source port, destination IP address, destination port. So how does that work? Okay, well, let me show you. Done that. Okay, so here we have a network, okay, and it is using the 10 range, 10.1, or sorry, 10.10.10.1, and which is private. 10.10.10.1 is private address, yeah. So we have an ISP here. Let's say this is Sky. It's easier to write Sky because only 3 letters. Now this is our company router. RA is our company router, right? We have a link to Sky. So we can't see Sky's router, but let's say, for example, here, it's here, right? And Sky is an ISP. So your Sky ISP will have a load of they will have a lot of IP addresses that they can hand out, that they can lease. So we as a company will contact Sky and say we want an internet connection. We want a business link to the internet to serve our company here. Now, let's say, for example, we could have 250, let's say 200 staff. Okay, and we have a /24 to cater for that staff. So they're everywhere 10.10.10.0/24. Okay, we contact Sky and say, can you give us one public IP address? And Sky turn around and say, yeah, we're going to give you 64.10.75.34. That is your address to use for the duration of the lease. This is unique to your company. This is unique to our company. 64.10.75.34. So what you will actually do is, in terms of your configuration, let me zoom in here between, this is our router here, and this is Sky. So you're going to have a link. So it could be that, I don't know why I use 64.10.75.34 because it's quite long. So 64.10.75.34, and over here 64.10.75.35. So here and here. So basically we are connecting to Sky, and usually it's going to be a /30. Okay, now actually this would not be a /30, 28, 30. Yeah, no, this would not be a /20, 32. So it would have to be 33 and 34, but it doesn't matter. Let's say it's a /29. Doesn't make a difference anyway. So basically both of these IP addresses are within the same network. Yeah, this link here and this link. And Sky have said, when this is a unique to our customer, to, let's say we're selling phones, phone.ie. So Sky say any links to 64.10.75.34, it's going to tell the internet that send them across to me. So Sky will say, hey, because Sky own this whole range. So let's say Vodafone over here, it knows that if it receives a packet to 64.10.75.34, it's going to send it to Sky, because it'll say, oh, that's Sky's IP address. Okay, so each ISP knows what of their peers, they don't have the full routing table. They use BGP to have the full routing table. So Vodafone will know that Sky has the whole range of 64.10.75. Okay, we'll talk, that's another class, BGP. Okay, so the point I'm getting across here is we've got one public address, one public IP address, 64.10.75.34 that we got from Sky. We have a private address range, 10.10.10/24. Private address, 10.10.10. Anything with a 10 is a private address. And we can have 200 staff overload to one IP address. Our 200 staff can use the same IP address for the purpose of browsing the internet. So if host A wants to go out to the internet, its source IP address is going to be 10.10.10.10. When it hits our router, our company router will take the source IP address 10.10.10.10 and it will change it to 64.10.75.34 and send it out to the internet. For example, CISCO.com. CISCO.com will respond back to not 10.10.10.10, but will respond back to 64.10.75.34. When that comes back in, the router will retranslate it or rechange it from 65.10.75.34 back to 10.10.10.10 and send it on to host A. Okay.
So if 200 staff all went on the internet at the same time,
Yeah. And all go to the internet.
they're all go using the same IP address.
Using the same one public IP address. Yeah.
Okay.
And don't worry, I'm sure you have more questions. I'm going to go through why and how it all works. This is the reason why we haven't run out of IPv4 addresses. You know, because of port address translation. Let me change this here 1 second. I want to change this to paint. Right. Okay. So first of all, before we look at this, we've got two different kind of zones. Okay, you might have heard of these zones before. These are kind of used in firewalls and stuff, and out in companies. And there's different names that you can use for them. You've NAT inside, which is typically inside your company, and you've NAT outside, which is outside your company. Inside, which is inside your company. Outside, which is outside your company. Okay, another word for these is trusted and untrusted. But Cisco say inside and outside. Juniper is more trusted and untrusted. So trusted would be trusted in your company, untrusted would be the internet, okay? Because you shouldn't trust anybody out on the internet. Okay. So you got trusted and untrusted, inside and outside. Think of this S000 is a front door to your house. Okay. And as you're going out, the internet sees you, or the world sends posts to you. They send it to your front door's address, which is 64107534. Okay. And then you got individual names. A is Anne, B is Barry, and C is Charlie. Okay. And what happened is gets to the door, and then whoever receives the post will look and go, oh, this is A, this is B, this is Charlie. Okay, kind of. We'll go into more detail. Okay, so we got host A is going to cisco.com. So it's going to open up a browser. It's going to say www.cisco.com, right? So the source IP address is going to be 10.10.10.10. The destination IP address is going to be what Cisco resolves to. Okay, and we'll talk about DNS in a number of weeks. So Cisco, if we type in www.cisco.com, routing tables, routers do not know what cisco.com means. So that has to be changed to an IP address. So DNS takes cisco.com and it resolves it to 74574319. Okay, so the source IP address 10.10.10.10, destination IP address 74574319. Okay, some terms you need to know. Inside is inside your company. Local is your private IP address. Okay, local is your private IP address. So you've got local and global. Global is public. Local is private. Okay, so you got inside local, which is inside your company, and local is your private IP address. The private IP address, which is 10 or 192 or 172.16. Global is your public routable IP. Okay, so we say host A. One sec. Let me just actually 1 second. Take this here. Way down here. Okay, that makes sense. All right. So we got host A here, and Source IP address of host A is 10.10.10.10. 10.10.10. Source port is 5097. Okay, where are we getting the port number from? How does a device get a port number? The operating system. My operating system here assigns a port number and it's in sequence to the next packet that's established. Okay, so the operating system is responsible for putting all of this together. So this one here, source IP address 10.10.10.10, and source port 5097. Destination IP address, well, what Cisco is, which is 74.57.43.19. Destination port says port 80, okay, because it's HTTP. Okay, so this packet here it's going to go out to the internet. Now, the ISP host A knows that this is going out to the internet. How does host A know that? Because, well, there'll be a default route to send it to your default gateway, which is 74.57, which is going to go to, let's say, the IP address of the default gateway is 10.10.10.1. So this is going to go into your local router. And let's assume that is already set up, or port address translation is already set up. So as this hits my router will take the source IP address, which is 10.10.10.10, port 5097, and we'll have this a table, a NAT table, okay? So this is a NAT table that it keeps. And it's stored in its RAM, it's stored in its cache. Okay, so it'll take 10.10.10.10, 5097, and it'll put that, say, there's my inside local address, my inside my company, local, my private IP address. And then it looks at the destination, 74.57.43.19, and says, okay, you need to go to cisco.com. But before it does that, it will take the source IP address, which is stored there, and it will change it from 10.10.10.10, 5097 to 64.10.75.34. I'll put that in red maybe. 64.10, no, 10.75.34, port 5097. And we'll track that as well. So that is the inside, it's inside our company, but it's a global public IP address. Okay, so 64.10.75.34, port 5097. Okay, outside global, which is externally, global is the public IP address of cisco.com. So it'll track that as well. So it'll say 74.57.43.19, port 80. Okay. So this here now goes across. It's here at this stage. Before it goes out to the internet, this packet gets changed. You can see what's changed. Does that make sense? You can see what's been changed. The source IP address has been changed from a private IP address, 10.10.10.10, to a public IP address of our serial interface, 64.10.75.34. And then this gets routed out to cisco.com. Okay, goes into cisco.com, cisco.com receives it, right? Now, what does cisco.com need to do here? Cisco.com needs to respond back with a web page. Okay, so it's going to respond back with a web page. Just delete all this. This is the reply back from cisco.com. Let me just, sorry guys. So yeah, this goes over to cisco.com, cisco.com. So let's see if I can just do this here. This is cisco.com's response back. So the source IP address now is 74 .57.43.19. Source port is 80. The destination IP address is going to be 64.10.75.34. Destination port number is 5097. Sorry, did somebody say something?
No, it was me. Sorry, it was just I hit mute as I was talking. Sorry.
Okay, no, you're right. Okay, so everyone see here, right? This is the response. This is the, so I sent a HTTP GET message. I was getting a web page from Cisco.com. This is Cisco.com responding back with a partial HTTP page. So this here makes its way from the internet, from Cisco.com's web server to 64.10.75.34. The thing is, the internet knows that this goes to Sky. Okay, so this is, oh, that's Sky. Sky owns 64.10.75. So we're going to send it to Sky. This goes into Sky's sort of company, and Sky say, okay, well, which one of our customers has 64.10.75.34? Oh, that's phone.ie. So let's send it to the phone.ie router. So this goes across into our router in here on this interface. Our interface is 64.10.75.34. So it's responding back to this packet in the router, responding back to the router. Not host A, to the router. 64.10.75.34, 64.10.75.34. Okay. As this packet comes into that IP address, the router takes this packet, checks against its NAT table, which is already got stored in its cache, and says, who originally requested 64.10.75.34, 5097. You see, 64.10.75.34 tells our routing nothing, because every packet coming into the router is going to be 64.10.75.34. It needs some way of identifying host A from host B from host C, of knowing who internally sent that request. And how it does that, it looks at the port number and it checks that against its NAT table. So the inside global IP address isn't going to really tell the router anything. 64.10.75.34, 64.10.75.34. Then it looks at the port number 5097. This will be unique, or should be unique. Well, it doesn't even have to be unique. So 5097, and it says, well, who originally requested 5097? Because this is NAT table. This is in the cache. This is stored in its RAM. So 5097 was initially 10.10.10.10, 5097. So what has to happen? This packet, 64.10.75.34, the router takes this 64.10.75.34 and it changes that IP back to 10.10.10.10, 5097. So it goes here, it sends over here. Clear as mud.
Yeah.
Good.
That's okay.
Any questions? So how does it work? Where's the magic in it? The magic is the fact that we have one IP address, 64.10.75.34, that can be shared across, let's say, what we say, 200 hosts. 200 hosts here. How? By port numbers. 5097. What uniquely identified this device here was 5097. We didn't have host B going to Cisco.com with 5097 or host C. They all were going from 64, 10, 75, 34. But what they separated on the NAT table was host A was using 5097. Look how many port numbers we can have. We can have 64,000 port numbers. Like we're up here 50733 all the way across. This is going to go as far as 65,536 before it gets reset. So we're using the port numbers to further split the devices. I've worked in a company with 1,000 users, all using one public IP address. 193.95.170.99.
So would bandwidth come into play then there as well?
Sorry, Graham?
Would bandwidth come into play? If you, I say you had 1,000 users using one public IP address.
Would what make a play?
Bandwidth.
Bandwidth. Well, oh yeah, well, it wouldn't. Bandwidth wouldn't make a difference per IP. You know, bandwidth is. You know, you need to have enough bandwidth to cater for 1,000 people all going out the internet. So it would be the size of the connections. The internet would really be for bandwidth. But from here, it's not going to make a difference in terms of your IPs. One kind of thing that kind of, let me see if I can get this, would be, we looked at that there. Yes, okay. This is one thing that kind of threw me when I was learning first, is what would happen if you had, so we're like, this is all working on the premise that we have 5097 was available, was unique to host A, okay? But it might not necessarily be unique to host A, because it's quite likely, especially if you have lots and lots of users, that someone else might be using the port 5097. You know, who assigns these port numbers? Host A's operating system assigned 5097 to host A. It's not going to be able to communicate with host B and host C to make sure 5097 is exclusive to it. So it's very likely that we have host C, for example, going to Yahoo that might be using 5097. What happens in that instance? Source IP 10, 10, 10, 30. Source port 5097. Destination IP. We're going to yahoo.com, so we say 67.14.35.20. Destination port 80. Yeah. Let me just kind of see if I can clean up this chicken scratch here. Okay, so what happens? This is going to go into the internet or go to my local default gateway. I'll say switch A into the router. Yeah. So this is a router here, and the router sees this and goes, "Oh, I need to take 10, 10, 10, 30 and change it to what IP address? 64, 10, 75, 34. So it does that. So it takes 10, 10, 10, 30. And it changes it to 64.10.75.34. And then it looks and says 509. So it has this here. So it says 64.10.75.34. And then it looks and says, oh, 5097. I can't use 5097 because 5097 is already being used by host A. It's already been used by, remember this NAT table, the router keeps this NAT table. So it says 64.10.75.34, 5097. That inside global IP and port number combined is used. The IP will always be 64.10.75.34. So the router says, I just need to use something that is not being used. I need to use something that is unique. I need to use a unique inside global port number. So it looks at the next available one. It doesn't matter. It doesn't care. It could be 6,500. Okay. So it says I'm going to keep 6500 and I'm going to keep a record of that. So this 5097 gets changed to 6500. This goes out to yahoo.com. Yahoo.com see it and then say, I want to respond back. So what happens? Everything gets flipped. The source, so everything gets flipped. So the source IP address is 67.14.35.20. Actually, I should really finish that table here. Oh, one sec. Oh, this is going to be down here. So source IP address 67.14.35.20. Source port is 80. The destination IP address is going to be 64.10.75.34, 6,000. So it's just responding back to 64.10.75.34. Yeah. It's going back into Yahoo. Or it comes back into my internet, my router. This is my company router. My company router then looks at this and says, okay, 64.10.75.34. That says nothing because every packet that is coming into the router will be destined for serial 000 because this is public. It's publicly routable. So 64.10.75.34 says nothing. 6500 tells the router that that initially was 10.10.10.30, 5097. So it takes this 6500 or takes this 64.10.75.34 and it changes it to 10.10.10.30. Takes this 6500 and it also changes it to 5097. So it deletes both. So it takes 64.10.75.34, 6500 and changes it to the IP address and port number combination. By the way, that's called a socket. To this guy here. Mode the range here. And then this can go off the host C here. And that's it.
Is the NAT table age out, does it?
Sorry.
The NAT table age out.
I can't hear.
Sorry, does the NAT table age out?
Yes, it does. It times out. So if it hasn't received a response, it would be like seconds that it'll just be removed. Yeah.
Okay.
There is definitely a timeout, and it'll get cleared as well. So because there's a timeout anyway. When you send a HTTP request and it doesn't get a response back from a web server, it will bring up like a 404 error anyway within a certain amount of time to say, look, can't reach the server.
Thank you.
So yeah. There is a lab on that, but what I might do is keep that lab for tomorrow. We'll do that lab for tomorrow, and packet tracer together might be good. And it's 8 o'clock, so I might start our new one now, which is IPv6. and see how far into that we get. Okay, so we'll start now. Yeah, I'll do half an hour of IPv6. We'll take a 15-minute break, and then we'll do the rest. And we'll do a NAT lab tomorrow on packet tracer. Okay, so I'm going to talk about IPv6 now. The fun of it all. Okay. Right, so we were saying earlier on, go back to our IP addresses, was that you've got 4 billion IP addresses. It is, so, you know, let me just, this is an example of your IPv4 addresses, yeah? And we went through this already. You've got your IP address and your subnet mask, and you've got your slash notation. Forget about the subnet mask, concentrate on the slash. 10.5.11/8, 150.51.233.1/16, 220.1.50.63/24. Okay, an IPv4 address is a 32-bit IP address. 32 bits give us altogether a combination of 4 billion. Where are we getting that number from, 4 billion? So we take this calculator and we say standard is not enough. I think I need a, there's a scientific, yes. So I say 2 to the power of 32. There's your billion, 4 billion. Okay, that's where you get your IP address. So basically 2 by 2 by 2 by 2, and you keep going, and you mention 2 by 2. 2 multiplied by itself 32 times. Does that make sense? Yeah, I hope. Like 2 to the power 3 is what? Two by 2 by 2. 2 multiplied by itself 3 times is 8. 2 to the power 4 is 16. 2 to the power 5 is 32. 2 to the power 6 is 64. 2 to the power 7 is 1, 2, yeah, and so forth. Yeah, I think I might skip one there. But you get the gist, yeah. So 32-bit address gives it a 4 billion. So when they were making IPv6 addresses, they said, well, we're going to make our addresses bigger in size. So the more bits we give an IP address, the more combination we can have. So they take your IP address and they change it from IPv4, which is 32-bit, to IPv6, which is 128 bits. So IPv6 address is 128 bits. And that gives us this amount of addresses. Much, much, much more than your 4 billion. Yeah. Enough to say we'll never run out of IPv6 addresses. And I know somebody out there, one of you is thinking, oh yeah, about an hour ago we said that about IPv4, and look what happens. We had to use NAT and PAT. Now we're in IPv6. How long is it before, you know, with IoT, Internet of Things, before you start, you know, you put an IPv6 address on a light switch, and one on my fridge, and one on my oven, and one on my computer, and one on my phone, and you know, we'll start eating into these IPv6 addresses fairly quick. No, we won't. You won't even scratch the surface. The amount of IP addresses, IPv6 addresses here is phenomenal. You know, this term is called 340 undecillion. 340 undecillion addresses. Okay, so to put it to, you know, to kind of put it to context, to give it some sort of context behind it, right? what is there? We've got 8 billion people in the world, or in the universe, or in the universe, on Earth. Let's say, for example, to keep things nice and round, let's say we have 31 billion, because this kind of just fits in, right? We got 31 billion, yeah. Let's say we've got 31 billion people on Earth. Just a little bit smaller. Yeah. So 31 billion people on the planet. Out of if there was 31 people, which was what, or maybe 4 times the population that we have currently, each one of those 31 billion would have this amount of addresses per man, woman, and child, each unique public IP addresses. We're not going to run out of IPv6 addresses ever. What will happen is, which is far more likely, we're going to just blow the shit out of each other in some nuclear holocaust. And you know, doesn't matter if it's 100 years time or 1,000 years time, it's bloody inevitable. Especially the way things are going. I don't have much hope for us as a species, to be honest. Anyway, that's different conversation altogether. That's, yeah. All right, but yeah, so we're not going to run. Or the other thing is, maybe we get invaded by some interterrestrial or extraterrestrial species that wants to use these 340 undecillion IPv6 addresses. But no, we're not going to run out of them anytime soon. To put things into a context again, another kind of scale. Let's say your IPv4 addresses. Let's say, what's that? The size of a maybe size of a golf ball. Maybe that's a golf ball there. I know it's a screen, but kind of fits. Yeah, there's a golf ball there on the screen. Yeah, if that was your IPv4 addresses. So you had 4 billion IPv4 addresses, was using a scale the size of a golf ball. By the same scale, what would your IPv6 addresses be? What object?
The moon.
Bit bigger.
The Earth.
Bit bigger.
The sun.
The sun. The sun.
The universe.
Oh yeah, well, yeah. Well, the sun. Yeah, well, I don't think we can. I don't think we can measure the universe, but the sun. Yeah. So you got an IPv4, which is a golf ball. So you compare the size of a golf ball to the size of the sun. That's by scale the size of IPv4 addresses, or the amount of IPv4 addresses comparative to the amount of IPv6 addresses, and you kind of get the gist. Okay. So you got it. We're not going to run out of IPv6 addresses. One of the big differences is your IPv6 addresses are going to be hex characters. So you've got IPv4, which is 192.168.10.5. IPv6 is hex characters. So 8 groups of hex characters, 4 hex characters in each group. Okay, so what is a hex character? Remember, a hex character can give you any combination between 0 to F. 0 to F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F is your hex characters. Okay. So how many bits in one hex character? So how many combinations do you get here from 0 to F? How many values do you get?
16.
16, yeah. So one hex character, you can have 16. Now remember, a bit, just to go back to a bit is either a 1 or a 0, or 0 or 1, yeah? So 16, yeah? So you go 4 bits. 8, 4, 2, and 1. So 3, 7, 8 is 15. 15 combination, 15, but remember 0 to F is 16 values, so you count to 0. So it takes 4 bits to make the value of 16. Okay. So you've got 16 bits, or it's not 16 bits. You've got 60. Yeah, you've got 16 bits here. 16, 16, 16, 16, 16, 16, 16. Yeah. Gives you 128 bits. So so you got 8 groups. 8 multiplied by 16 is 128. Now, what else we do is they take these IP addresses and they change the colons. So 2001 colon 0050 colon 0000 colon 0000 colon 0000 colon 0AB4 colon 1E2B colon 98AA. Yeah. So there's no dots anymore. 192.168. The dots are gone and replaced by a colon. Okay, and another thing, you don't have your conventional subnet mask. So let's say we have 192.168.10.3/24. Your 255, the zeros are gone because it's just too hard to manage. Instead, they use the slash notation. So you still need, routing devices still need to know this is an IP address, it's an IPv6 address. How much of this IPv6 address is dedicated to the network part and which is dedicated to the host? So usually it's split in half. So you'll see something like this, /64. So when I see this as /64, what does that tell us? How many of these groups? Where is the network? Where's my red line? My red line, where am I going to make that? Here, 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 here.
On the fourth
On the
left.
fourth, exactly, here. So this is my network part, and this is my host. And I get it. This can be very confusing, but think back to here. Okay, this is your network 2001 0050 0000 0000. That's the network part of this address. The host part is 0000 0AB4 1E2B 98AA. If you look at IPv4 192.168.10, that's the network part. 3 is the host. That there is the same as this over here. The only difference is this is bigger and you're using hex. But it's the exact same concept. /24 tells you the first 24 bits represent the network part. /64 tells us the first 64 bits represent the network part. Now you could change that if you wanted. We could change that to a /, let's say 80. If that was /80, what would happen then? The red line would be here. The host would be here. But typically, it's usually /64. But you can change it from a /64 into a /80. Like you can change this from a /24 into a /26 or /whatever. Any questions on any of that?
All good.
Okay. So there are 2 rules. I'm going to go through them. Eliminate group of consecutive zeros and drop your leading zeros. Okay. So let me I'm just going to actually put this over here. For example, I'm just going to get Notepad. So first rule. First rule is we don't talk about Fight Club. Anyone? I was like saying that. I only seen the film there yesterday or a couple of days ago. Still as good. Okay, rule number one, we eliminate groups of consecutive zeros. So let's say we got this IP6. Okay, so 2001 colon 0050 colon 0000 colon 0000 colon 0000 colon 0 actually colon 100 A 0000 1 2 3 4 5 6 7 colon 0000. Okay, 1 2 3 4 5 6 7 8. Okay, so first rule is you can eliminate groups of consecutive zeros. Is there? Eliminate groups of consecutive zeros. You can't get rid of them. You can have to replace it with a double colon. So now the rule is eliminate groups of consecutive zeros once. You can only have one double colon per IPv6 address. That's not a happy. Let me just get rid of that there because it looks like a bloody emoji. So you can only have one double colon. So when you see a group of zeros, you can take these here and you can change it into here. Now, you can only have, and they have to be consecutive. So you have a choice. Do you swap these three here with a double colon, or do you swap these two here with a double colon? Well,
Three.
Yeah, you eliminate the three. Why? Because you're shortening the IPv6 addresses. So, by the way, these rules are completely valid. They're you don't have to use them. They're only there for humans. They're only there for us to use it to make our lives easier. A router doesn't care if it's shortened or long. A router's not going to say, "Oh God, you have to give me a longer IPv6 address now. I have to, or short. I have to change it." It's nothing to a router. You know, we like to do it. So 2001 0050. There's another thing as well. Do everybody see why we can only have one double colon?
Stops confusion.
It does, yeah. Why? How does it stop confusion?
I want to know where the
Zeros
zeros actually started and where it stopped.
Exactly. So let's say if you have this, this is the wrong way to do it, but I'm just going to show you. 100 A. Okay. So double colon. Okay. So this here, I've basically used two double colons right here and here. Now you're going to have a router here. Okay. So you're going to have a router that's going to take. So let's say router that's going to look at this IPv6 address and is going to say, okay, this address here. Now this router here has to take this address and re-lengthen this back into its original format. So it says, okay, well, okay, there's three groups here, 1, 2, 3. So therefore, there should be another 5 groups missing. But the router doesn't know how these 5 groups are divided. Is it, for example, is it
3 zeros and 2 zeros, or
4
2
here,
zeros,
4 groups of zeros here, or you know, 1 here, or is it 1 here and 4 here, or is it, you know, 2 here and 3 here? It doesn't know. It has no idea. So, like you said, to eliminate confusion, you only have one double colon. So what can you do? Can you do anything with these then?
No.
The second rule, you can drop your leading zeros. So you can have 0, 0. Now you need to keep a 0 in there, but you can drop the other zeros because you need to, because again, a router now, so if a router takes this here, okay, 1, 2, 3, 4, 5, you need to put in these zeros, otherwise the router is not going to know how many groups of zeros this is here. Now it knows, there's no ambiguity. It knows 100% that this double colon represents 3 groups of zeros. That makes sense? So 2001, 0050, 000000000000. So these 3 groups of zeros are here. 100A, 100A, 0000 colon 0000 0 colon 0. Is there any way of shortening this again? 2001 colon 50 double colon 0A 0. You can drop your leading zeros. So there's 2 kind of things you can do, drop, but they have to be leading zeros. So whenever you see a 0050, they can be just dropped to 0. It has to be leading though. But we do that with decimal all the time. If I see this 305, what do I normally do? I just go 305. There's no difference. That there is the exact same as saying 305. I can't drop the 0 in the middle because that gives my number structure. 305, 3. I can't drop that, but I can drop the leading zeros because they don't mean anything. Okay, so you can eliminate group consecutive zeros, or you can replace group of consecutive zeros using a double colon, but you can only have 1 double colon in your IPv6 address. And you can drop your leading zeros. Instead of having 0050, you can just have 0. I can't do anything with 2001 because they're in the middle of those zeros. Any questions on that, guys?
Oh, good.
Okay, cool.
Nope.
Okay, I got a question for you. Have a look at this, and you can send me in chat, private chat if you want. Tell me which ones are valid. Which are valid, A or B? They could all be valid. None of them might be valid. One of them might be valid, 2, 3. How many and which? Not just how many, which ones. Select which ones are valid. Okay. Do you want to see it bigger or? Oh, close that there. All right, interesting. A couple of ones already coming in. Well. People are changing their minds. Couple of fence sitters. Okay. All right, guys. Right. Let's have a look at these. Oh, actually, one person I think got it. Stephen got it. Kind of changed his mind at the very end. Okay. Right. Okay. What about A?
No, definitely not.
Why not?
2 double colons.
2 double columns gone straight away. Yeah. So we can't actually. Yeah. So you can't do that. Undo. Okay. You got double colon there, and you got a double colon there. You can't. That's not allowed. What about B?
1, 2, 3, 4, 5, 6,
I said there's only 7 octets.
7.
7. The 7
Yeah.
groups, and there's no double colon. You can't. It has to be 8 groups. 1, 2, 3, 4. That's fine. 6, 1 is fine. That just means it's 0, 0, 6, 1. That's no problem. So 1, 2, 3, 4, 5, 6, 7. No, that's wrong. Yeah. So A and B are wrong. What about C?
2, 3, 4.
5.
Big.
And then you got a double colon. So
They could be consecutive zeros.
yeah, that's fine, isn't it?
Yeah.
Any issue with C?
There's a G in it. I only copped it there now.
Yeah.
Yeah,
There's a G.
Yeah,
There's a D,
only copped it there now.
yeah, it's a sly one.
Well done, Stephen.
Well done, Stephen. Well, Stephen had it, and then he just chipped in at the very end. Well, actually, wait, C isn't a valid one because yeah. So what about this one?
Yeah.
Well, it's valid, yeah. This here is
Consecutive zeros.
0, 0. So basically, this is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0,
15 zeros. 1.
Yeah. And another way of I'll use power. I don't want to be powered off. It is your loopback. It is your IPv6 loopback address. So you have ping 127.0.0.1. There's IPv4. You've got your IPv6 equivalent of double colon 1. Okay. So you can get really geeky t-shirt that says there is no place like 127.0.0.1. There's no place like home. And you get really, really geeky t-shirts that says there is no place like double colon 1, which is basically this is your IPv6 home address. All right. It's coming up to half. I don't want to talk about configuring IPv6 addresses and your different types of things yet. Get yourself a coffee because it's a kind of difficult concept to get through. Okay, so we'll look at that in 15 minutes time. Okay.
Cheers.
Thanks, guys. I'll see you at quarter. Yeah. Cheers.